am not recording. Now we're recording. Okay, thank you for bringing that up, Andy and Bruno. Where was I? Yes, so we will look at these two sections of pipe in the review of the exercise. I will not look at the rest of the pipe because, again, it's all the same calculation. So the first thing that I'll do here on my sketch is take the relevant information off of my drawings. So I'm looking for rim and invert of CB1, of manhole D2, and of manhole D1. So I'm straight copying off of my drawings. So looking at my drawings, I see they're very tiny. So catch basin 1, we're told rim is 62.6. And the invert of the pipe is 62. So for manhole D2, next in line, we're given the invert. So we've got an invert in and an invert out. So for our, maybe I'll show both of those. So in is 61.68. So 61.68 meters. That's the in pipe. And the out pipe is 61.63. That's out. So in meaning on the inlet side of the manhole, and out meaning on the outlet side of the manhole. Once I'm done with these sketches, I'll scan them and upload them to Learning Hub so that you have them. So what's the rim for the manhole? That doesn't show in the plan. It shows on the profile. So looking down at the profile, it says the rim is 63.3. So that's manhole 2. So then we do a similar analysis of manhole 1. So rim is 63.3. And then we'll have 2 inverts. We're only going to use 1 invert because we're only doing this section of pipe that applies to this manhole. So we'll only actually look at the invert. So the invert of the in pipe is 60.97. So that's in. And just for completeness, the out is 60.92. Okay, so those are the rims and inverts that were given directly off of our drawing. So I haven't calculated anything yet. I will mention that the length of the pipe between manholes is actually just between these 2 manholes is given on the drawings. You don't have to scale it. It's in the profile. It tells you 66.59 meters of 250 millimeter diameter storm. So I rounded that to 66.6. For the catch basin leads, you had to scale those. You had to measure those off of your drawing. So I scaled for CB1 lead, I scaled 32.5. If you were slightly different than that, I didn't mark you wrong. As long as you were in the ballpark within a meter or 2. It was fine. Okay, so we'll come back to that. So this is what our trench cross section will look like at CB1. So we're told, I'm just looking at the sketch so this sketch that we just did, I'm looking at that. So we've got an invert of our pipe at the catch basin of 62.0. So we'll say 62.0 meters. The rim again, off our sketch that we just did, is 62.6. Now, you were told in the question to not calculate volumes to the finished grade or the rim elevation. You were told to calculate to bottom of the road structure, in other words, the bottom of the subbase. So you had to deduct that distance off. So what was that distance? You're told on the cross section of the parking lot that the road structure is 65 asphalt, pins down, 100 a base, and 200 subbase. So add those up, that's 0.365 meters is your road structure that you would deduct from this total height calculation. So here are the, for each of these cross sections that we're going to look at, we're going to calculate these 4 end areas. Once we have end areas, then we will calculate volumes after that. Yes, you, 365. So excavation, what's excavation? So I'll quickly draw that in here. So the green, there's our excavation. Excavation is green. So all we're simply doing here is calculating this triangle, that triangle, and then this rectangle in the middle. So you don't have to calculate the entire thing at once. So break it into easier shapes that you can calculate areas for. We are using a 1-to-1 slope. That was also mentioned in the question. So that's important. So what's our depth of excavation? So it's 62.6 minus 0.365. Let me get my calculator. So 62.6. So minus 0.365. So then subtract the invert of the pipe. So that's 62. So that leaves you from bottom of subbase to invert of pipe of 0.235 meters. Okay, but we want to go 100 deeper for the bedding layer, right? Remember, we need a minimum of 100 of bedding. So we want to add 0.1 to that. So we're actually going to go down to here, and we're going to call that 0.335 meters. So, so what's our width here? Now, because we're calculating a catch basin trench, our pipe is only 200 diameter. So 200 CB lead. So what's our minimum width here? So a D, which is 0.2 plus 0.45. So our width here is 0.45 plus 0.2, so 0.65. So we can calculate that rectangle now. So then we need these triangles. So if I draw another dimension line over here, so this now goes to the invert. That's what we used to have over here, but I changed it. So it's simply 100 millimeters less than that number. So it'd be 0.235. So this here, 0.235, which means this dimension is the same because we're a 1-to-1 slope. However deep we are, that's the width across the top also. So this here 0.235 meters, of course, for all these. This is also the same. Okay, so for excavation, what do we need to calculate? So let's do the square or the rectangle in the middle first. So 0.65 times 0.335. So that'll give us the area of the rectangle. So then we have two triangles, two of the same triangle. So area of a triangle is base times height divided by 2. But because we have two of them, we're not going to divide by 2. We're just simply going to go base times height. So we'll add 0.235 times 0.235. That'll give us the end area of our excavation in green. So if I do that calculation, so 0.65, 0.335 times, and then we'll go 0.235 times 0.235, add those together. So 0.273. That's the area of the trench excavation at the catch basin. So we'll go on to the next one here. So the bedding layer, well, we've basically done that. So it's the width, so 0.65 times this depth here of 100. So 0.65 times 0.1 is 0.065 square meters. Okay, so that's the little hatched area in there that I've got. So now let me go with the cover. Highlight this in blue. And up this side. So the cover is the rest of the bedding. So it's from the invert of the pipe all the way up to 300 millimeters above the pipe. So you can do a similar triangle calculation here and a similar rectangle in the middle. So what are we looking at here for height? So if I try to draw this inside here. So we've got our pipe is 200 plus another 300. So that's 500 high, so 0.5 meters. And we already have the width. So then what does that make this width here of the triangle? It's the same as that depth, right? Because again, we're 1-to-1 slope. So if we're 0.5 meters deep, this triangle here is 0.5 meters wide also. From there to there. Okay, so area of the blue then is 0.5 depth times 0.65, and then we would add the triangles. So there is a quicker way to calculate this in one step. So instead of doing this square and then do 2 triangles, we could simply do this area here. Because this additional piece here is the same as that triangle. So that would be flipped over to there. So if we did that width times that depth, it'll give us the area that we're looking for. So let's go ahead and do that. So this width is 0.5, so this is also 0.5. So 0.5 plus 0.65. So cover, so 0.5 plus 0.65. So that's our width, and our depth is 0.5. So we're multiplying by the depth. So times 0.5. So on my calculator, 0.5, 0.65, add 0.5 deep, So that is 0.575 square meters is our cover. Now we need to deduct the volume of the pipe out of there. So we need to calculate the area, the end area of the pipe. So area of a circle, so area of a circle is pi r squared. So pi is 3.14. R is the radius, so half of the diameter. So times 0.1 times 0.1. So 0.1 times itself. So if I go 0.1 times pi, so that's 0.03. 0.03 square meters. We need to deduct from our cover area. So if we subtract 0.03 square meters, so 0.575, 0.03 minus, so that leaves us with the overall cover amount of 0.545 square meters. Notice these are all square meter calculations. So we're calculating areas here. We calculate volumes next. So what's the backfill? So you could go ahead and calculate this area, or you could do some quick subtraction. So again, two different ways to do it. So I'll go with subtraction. So we're going to take the overall excavated volume. We're going to subtract the blue, and we're going to subtract our little 100 millimeter thick bedding layer down here. Now, when you subtract the blue, you have to use the number before you subtracted the pipe area. Otherwise, you'll need to add it back in. So this is the number that I'm going to subtract. So if I write that down, so excavation was yeah, I just realized that there is no backfill, is there? So why do I say that? When we calculated our rim to invert and then our subbase to invert, we said we were 0.335 meters deep, right? So when we calculated our cover amount, we said our cover needed to be 0.5 meters deep based on this 300 above the pipe. This isn't drawn to scale, this cross section. So what that tells us is our cut depth of 0.335 is less than our cover depth of 0.5. So there is no backfill volume here. So our backfill is going to be 0. And actually our cover is no longer 0.5 deep. It's 0.33, it's 0.235 deep, which puts it just barely over the pipe. So let's revise that. If I grab a different pen here. So this here is going to be this number here, so 0.235. Our width doesn't change. This number will change. And this number will change. So if we redo our cover calculation, so I'm going to do it, I'll do it just below this first calculation of the cover. So I'll do it in blue right below here. So we now have 0.235, which is this. So we're adding to it the width here of 0.65. And then we said we were going to multiply by the depth of 0.235. So times 0.235. Okay, what does that give us? So 0.235, 0.65 add, 0.235 deep. So that's 0.208, so 0.208. Our pipe area doesn't change, so that 0.03 doesn't change. So we subtract 0.03. Leaves us with a correct cover volume, or cover area, sorry, of 0.178. So this one here is wrong. So if I draw an arrow here, that's the cover calculation. It's like this because our depth of bury for the pipe is so shallow under the subbase. So no backfill, it's all cover material. Okay, so we'll do the same calculation, or the same sorts of calculations at manhole 2. So we'll work up some end areas there. So let's do that next. So here's manhole 2. My red pen out. Okay, so our rim at manhole 2, again right off of our drawing, is 63.3. So again, our road structure, if that doesn't change, is 0.365. That's from before. So where do we go next here? I guess our width of the CB lead at the manhole, so this dimension here, so that doesn't change. We're still 0.65 meters. Because again, we're still looking at the 200 diameter CB lead. We're just looking at it at the manhole now instead of at the catch basin. So Ivan, your question is, how is it right if the storm pipe is 250? Well, the storm pipe, let me go back to this sketch. The 250 storm pipe runs from manhole to manhole. CB leads, so this is the catch basin. So a pipe that runs from a catch basin to a manhole, those are 200 diameter. They're smaller. So that's 200 diameter. This little piece here is 200 diameter. That's 200 diameter. That is 200 diameter. These should be 250 diameter. Yes, if we look on the profile, that's correct. So 250 runs like this, and all the CB leads are 200. So there's 4 of those. Okay, so we go back to, so we're at this manhole. Get back on the screen there. We're at this manhole. We're looking that direction at the catch basin. We're looking at this trench. So this one here, all the way along. We're not looking in that direction yet. So the width of our CB lead trench, again, is the same, 0.65. So what was our invert at manhole D2? So the invert in was 61.68. That was the invert. So we want to calculate depth here. I'm going to add in this other one over here. So we're looking from bottom of subbase. So this is our excavation depth. So from bottom of subbase to the bottom of our bedding layer, that height is what we're trying to calculate here. So how do we do that? So we start with the rim, 63.3. We deduct the road structure of 0.365, gets us to this elevation right here. And then we subtract the elevation of the invert of the pipe. That'll bring us down to this point. So that's 61.68. So that gets us to the top of the bedding layer. So then we need to add another, again, we're adding 100 millimeters. So we're adding 0.1 to get to the bottom of the bedding layer to increase that distance. So 0.1 add. So this distance is 1,355 meters. This one over here to the top of the bedding layer is simply this number minus 0.1. So that's 1.255. So 1,255. So what's the width of our triangle? Again, we're still using 1-to-1 side slopes. So whatever depth of the triangle is, that's also the width. So there's our depth, 1.255. So that's to there. I think. Okay, so let's look at the excavation here. So again, it's our green area. So you'll notice, as I stated before, there's a lot of repetitive calculations here. So what I do in when I'm estimating is I've created a spreadsheet that does all these repetitive calculations for me. I type in things like rim height or rim elevation, invert elevation, what the road structure is, and then Excel does all this calculation for me to speed up the process. Okay, so for our green area here, excavation, so we'll do the rectangle in the middle again. So we said 0.65 wide times 1.355 deep. So that's the rectangle. So then we need to add the two triangles. So 1.255 times 1.255. So 1.255 times 1.255. So that area is 0.65, 1.355 times, and then you'll add to that 1.255 times 1.255. So that gives you an overall excavation area of 2.456 square meters. So the bedding, again, the 100 millimeter layer below the pipe. So 0.65, 0.65 times 0.1, 0.065. So that's the same number as previously. So now the cover. Is there enough room to get the full 300 millimeters over the pipe? Previously, if you remember, there was not enough room. So what would that height be? So 200 pipe plus 300, so it would be 0.5 meters. We've got 1.255 meters of overall depth there. So there is room to get the full cover in, plus there's going to be some backfill here as well. Okay, so the cover, again, is the blue. So I'll do the quicker calculation. So this rectangle here I'll do. So let's just throw some numbers in so we know what we're looking at. So what's the depth? So it's 200 of pipe plus 300 of cover over. So 0.5. There's our width. And then this triangle width here is the same as the depth. So 0.5. Okay, so the width of our rectangle is going to be 0.5 plus 0.65. So 0.5 plus 0.65. Width, depth is 0.5. So multiply by the depth. That'll give us the end area of the blue, and then we'll need to subtract the pipe. So 0.5, 0.65, add 0.5 deep. So what we had before, so 0.575. Subtract the area of our pipe. Which was from before 0.03. So pi times radius times radius. So minus 0.03 square meters. So 0.545 is the cover area. So that's the blue. So now we're able to calculate backfill. So that'll be the area up here. I won't color that, that might confuse things. So it's between the blue and up to the green. So again, I'll go with a subtraction method. So I'll take the overall excavated area, which was 2.456 square meters. So I need to subtract the blue area without the pipe deduction. So that was this number here. So we need to subtract 0.575. And then we need to subtract the 100 millimeter layer below. So which was 0.065. So 2.456 minus 0.575 minus leaves us with 1.816. So that would be our backfill area. Okay, so let's go to kind of a summary page here where we can calculate volumes. So if I bring this maybe down here a little. So I think for the sake of time, we're only going to calculate volumes of the catch basin lead from CB1 to manhole 2. We're not going to do the calculations for manhole 2 to manhole 1. We're quickly running out of time here for today's class. So I'll put some numbers in here. So from our first calculation, we said our excavation end area was 0.273. So 0.273. We said the bedding, so this area down here, was 0.065. 0.065. The cover, we said, was 0.178. And then, So the backfill, we said there was no backfill at the catch basin cross section. So then we look at manhole 2, so the next item down the line. So we started at catch basin 1, so heading down to manhole 2. So at manhole 2, our excavation was 2.456. The bedding was the same. The cover was 0.545. And then we had a backfill here. It was 1.816. So then to calculate the volumes of those 4 items of this pipe, so this is a 200 diameter pipe. This one would have been 250. That's our length, right? We scaled that off of the drawings. So what you're doing is taking the end area at catch basin 1, adding it to the end area at manhole 2. So add those 2 together, divide them by 2, and then multiply by the length. Will give you the volume of that excavation. So let's go ahead and do that. So 0.273 plus 2.456 divided by 2. So that's the average end area between those 2. So multiply by the length, gives you 44.3 cubic meters of excavation. Same calculation for the bedding. Because they're the same number, we don't need to add them together and divide it by 2. So we can simply take 0.065 and multiply by the length. So that's 2.1 cubic meters. Cover is next. Notice we had less cover at the catch basin because the pipe was so shallow. It wasn't very deep. So we had 0.178 there. At the manhole, we had 0.545. Add those together, divide by 2, multiply by the length. Gives you 11.7 cubic meters of cover. And lastly, the backfill. So you don't just take this number, you have to add 0 to it, and then you have to divide it by 2. So you're taking this end area and dividing it by 2. So 1.816 divided by 2 times our length, 29.5. So this backfill would have been imported backfill. It would have been purchased gravel. It would not have been native backfill. Native being the excavated material. So that sequence of calculations, what I did with catch basin 1 and then manhole 2, and then doing the average end areas, multiplying by lengths, you repeat that process over and over again for each length of pipe. So we just did this section. So you would do the same thing here, same thing there, same thing there. You do the same thing for these shorter catch basin leads. So you can see that it's quite repetitive. Again, that's where Excel would come in very quite handy. Okay. So let's set that aside and move on to today's lesson. So we're behind the gun here on the time. Any questions? There was a couple as we were going there. Any further questions? So again, those 3 pages. So this one, and this one, I will scan and upload to the Learning Hub for your reference. I'll do that at the break. Okay, so let's jump into today's material. So we're going to look at a PowerPoint for earthworks. So the Oil Interceptor U it's the same type of calculation. Maybe I'll just touch on that quickly. See here, what do I have that we could use? So if I use something like this, so Oil Interceptor, so instead of a pipe, I've drawn a box here. So I'm saying that that's the Oil Interceptor. Now it's not square, it's a rectangle, right? The width is less than the length. So you're doing the same types of calculations for the Oil Interceptor as we did previously with the pipe. So you're calculating depth to bottom of interceptor. You calculate the bedding layer, the 100 millimeter thick layer. You're calculating one-to-one slopes up. You're doing similar widths for your triangles. Why don't we go ahead and do that quickly? So if I draw on here, so if I try to draw this in 3 dimensions, hopefully this turns out. So the Oil Interceptor is like a cube. So it's got a length, it's got a width, and it has a depth. So if I jump back to my week 3 and we see what the dimensions were given for that unit. So you're told in the question that it's 1.1 meters wide. The length was 2.6, and the height of the concrete is 1.8. So what we're going to do with the Oil Interceptor is we're going to create 2 different cross sections. So we're going to do a cross section looking at this narrow end. So our point of view is going to be this way. And then we would do one perpendicular to that, one looking this way. Because it's not square, we have to look at the box from 2 different directions in order to get an accurate end area for excavation volumes, etc. So if we look at this here now, so this would be one of the directions. So this cross section. So it's not a utility, it's going to be the Oil Interceptor. Now, this note down here where we have a minimum pipe diameter plus some distance for working room. That's what the additional 0.45 meters is for the crew to be in there working. So when you calculated for your Oil Interceptor, you should have added additional distance for length and for width when you dug the hole, when you excavated the hole, so that the crew could be working around down there. Now, I didn't mark anybody wrong for using a different number than I did on that width. So you can basically use whatever you want, whether it's 150 millimeters on each side, or 200, or 300, or 400, as long as you're consistent in what you do. So I'm going to go with 150 millimeters on each side. So if we look, we'll say looking in this direction is going to be my X direction. Looking in that direction will be my Y direction. So we're going to do the X direction, direction first. Maybe we can show this here also. Yeah, that works. So in our X direction, the width of the concrete is 1.1. So that width is 1.1. But we want some working room. So I said I was going to add 150 to each side. So 1.1 plus 0.15 plus 0.15 is 1.4. So then we're given on our drawing, or storm drawing, where did that go? There it is. We're told the rim of our oil interceptor was 63.3. We're told the invert of the pipe, we were given two of them. I'll go with the lowest one. 60.92 was the invert of the pipe. Now you were told in the information for the question that the bottom of the box, so the bottom of the concrete, is 1.05 meters below the invert of the pipe. So the distance from the invert of the pipe to the bottom of the concrete box is a further 1.05 meters. So that was important. It adds an additional 1.05 meters to your excavation depth. So let's calculate this depth here. And then we're still using 100 millimeters minimum for this bedding layer. So that's, for us, we're always going to have 100 millimeter thickness down there. So let's calculate this overall depth here. So we start with the rim. So 63.3. We're going to subtract the road structure of 0.365. Okay, that gets us down to this elevation here. So now if we subtract the pipe invert, it'll get us down to that elevation, so 60.92. So far our distance is from this red line here down to the invert of the pipe. So to get to the bottom of the concrete, we have to add 1.05 meters to our number. So 1.05 add. So yeah, you know what I did? I wrote down the wrong rim. That's why my number doesn't look right. My apologies. I wrote down the manhole 2 rim. The rim for the oil interceptor is 62.48. And is this right? No, it's not. It's 60.82. Good thing I looked. Okay. Okay, those are right. Let's start that over again. So rim is 62.48. Subtract the road thickness. Subtract So road thickness, so down to the 0.365, right? So subtract the invert of the pipe, so 60.82 gets us down to this point. So then we need to add another 1.05 to get to the bottom of the concrete. So that depth is 2.345. So 2.345 meters. So we could calculate the bedding. So 1.4 wide by 0.1 deep, right? You could do that. So what is this dimension up here? It's the same as this one. Again, we're going to use 1-to-1 slopes. So this is also 2.345. So now this is in the X direction. So using these dimensions that we've calculated here, so this width, this depth, this width, we would be able to calculate an excavation end area for our oil interceptor. The exact same method that we used with the CB lead cross section that we just did. Again, because we're short on time, I'm not going to get into that. I'm going to jump over to the other direction. So we just did the X direction. So we do the exact same thing looking at the Y direction. So again, our rim doesn't change, 62.48. So the road, 0.365. Invert our pipe is the same, so 60.82. So that depth doesn't change, so it's the same number that we just calculated. So I'm simply copying it off of the previous section that we did. Same thing with this number. So the only number that's going to change is the width down here. Because we're looking at the Y direction, so the length of the concrete here is 2.6. And I said we were going to add 0.15 to each end. So 2.6 plus 0.15 plus 0.15 is 2.9. So now we have, we know that length on this cross section, and we know that length on this cross section. So what is that? Let's write those numbers down. So in the Y direction, right? We're in the Y here. Let me make sure this gets on the screen. So Y direction, so we're looking that way. So the length of that blue line is 2.345 plus 2.9 plus 2.345 again. So if I add those numbers together, that's 7.59. So 7.59 meters is the length of that line. So in the other direction, so now we are, so we're X, so we're looking that way now. So the length of that blue line is 2.345 plus 1.4 plus another 2.345. So 2.345. So that's 6.09. So why does it matter? What do we need those lengths for, of those two blue lines? If we multiply those together, that'll give us the surface area, so looking down, of this excavation area. So looking down on that excavation, it'll be the area of the blue in both directions. So if we look at my three-dimensional sketch here, it's looking down on the top what the area of excavation is. So let's do that. So 6.09 times 7.59, so 46.2. So how does that help us? If we do a similar calculation with the bottom, so the bottom of our excavation are 1.4 wide. Similarly, in the other direction, we're 2.9. If we multiply those two numbers together, that gives us the area at the bottom of our excavation. So 2.9 times 1.4 is 4.06 square meters. So these two numbers here, that's the area at the bottom of the excavation. That's the area at the top. So again, we're simply going to average the end areas. If we add those two together, divide by 2, and multiply by the depth of our excavation, that'll give you the volume of the hole that you need to dig for your oil interceptor. So what does that turn out to be? So 4.06, 46.2, so add, divide by 2. Our excavation depth here was 2.345. Actually, we could go right to the bottom. We could add another 100 mm depth to that and get right to the bottom of the bedding. So we could go 2.445 for depth. So that gives you, let me just write it out here. So I did 4.06 plus 46.2 divided by 2 times 2.445 gives you about 61 cubic meters excavation. For the oil interceptor. So you can go through similar calculations to determine the amount of backfill that you need here, right? The backfill would simply be the total excavation minus the volume of the concrete, just the concrete. You could easily determine what your volume of bedding is, right? That area that we calculated down there times the depth, 0.1. Okay, so hopefully that answers your question. It can be complicated, yes. You need to be quite good at math to be an estimator. Hopefully all of you realize that. If you're not the best at math, you need to brush up on it, because I do math every day, estimating. Once you do it, a few hundred times, you get quite good at it. Okay, so we'll have to get through the PowerPoint relatively quickly because we have an example for today's lesson that we need to go through so that you understand how to do today's assignment. This goes back here. Okay, so let me share the PowerPoint screen. Share, here we go. Okay, can everyone see the number 5 earthworks on their screen, the PowerPoint? Yes, okay. So, earthworks. Okay. So we have a few photos of different earthworks operations going on there. So earthworks considerations. So some things to consider when you're doing an estimate that has earthworks on it. So some of these would apply to any estimate that you're doing, like who's the client. Of course, it reminds you there, the second bullet, to minimum performance in the contract. So again, as I mentioned last week, you must read every word in a contract document. So the specs, you must read every page. The drawings, look at all the drawings. Understand everything that's being asked of you. It's very important. How is the work sequenced? So things like the project schedule. So the client may have a sequencing schedule that can impact the most productive methods. So maybe they want certain parts of the job completed before other parts, so which force you to work on those parts first, so get them going first. It could have an impact on the way you price or you estimate the job. So it's important to be aware of scheduling requirements that are listed in the contract. So the next bullet there, where is the project? So is it a congested area, such as a downtown, building excavation, or is it out in the country? Are you building a highway way out in the country where there's hardly any traffic and hardly any pedestrians, etc.? So looking at the location of the job is also important. It impacts your productivities, impacts the size of the equipment that you can use. It impacts things like how quickly you can get gravel, how quickly you can dispose of spoil. So your dump truck loaded with the excavation has to drive, is it an hour to the dump site or is it 3 hours? Because of things like traffic. Do they have to stop at stoplights every 30 seconds? So the location of the job is very important. How big is the project site? So is it quite large? Do you have a number of hectares? Thousands of square meters of area that you can put your site office, and your equipment has an area to go, and you can stockpile materials, etc. Or is it really congested? Do you not have any room for any of that stuff? So any excavations, maybe if you don't have a stockpile area, an area to store it, maybe you need to get rid of it as you're digging it, rather than making a big pile and then loading it out when you have a sufficient large enough pile. So those things carry different costs with them. So the last one there, what's the project duration? So if you have 2 excavators and you have your own 3 dump trucks, is that enough equipment to get the job done on time? Or do you need to rent additional excavators? Do you need to rent bulldozers to get the job finished in time? So things like that need to be looked at. Do you need to hire additional crews, possibly at a higher hourly rate than your own personnel? So all those things need to be looked at. So what's the project schedule? So time of year can significantly impact productions. So for us here in the Lower Mainland, digging in silt and clay in the rain is basically impossible. It becomes just muck. You can't do anything. Your equipment gets stuck. You can't get trucks to your excavator. It doesn't work. So that's an example of time of year. The next one there, compaction in the winter. So because it rains here so much, compaction is usually not an issue. In the summer, you would have to hire a water truck to get the gravels wet. So your road gravels, for example, you would have to spray the road gravels with a water truck to bring the water content up. So there's enough moisture in the gravel in order to get the required compaction. In the winter here, it rains so much, you likely don't need a water truck. So there's a benefit to that. Other things like, is a night shift required? Do you have to work 2 shifts per day? You know, maybe it's 2 8-hour shifts or 2 12-hour shifts per day in order to get finished. Do you have to work weekends? So schedule that's listed in the contract is very important. We've seen through previous assignments that working overtime is costly. It costs more to pay people overtime than it does straight time. What is the scope? So are certain sizes and types of machines required? For example, if you have to dig a really deep hole, you know, that's 10 meters deep, and there isn't room to build a ramp down into the hole, maybe you have to dig the hole from the top. So maybe you need a long reach excavator. You know, that's an example of what the scope of work is, and do you have room to use different options for equipment? So the next one there, are we experts, or do we have very little experience in the scope of work that we're pricing? So if you're a road builder and you've built 1,000 road projects and you're bidding, so you're estimating another road project, you would likely call yourself an expert in the road building field. If you've never built a road, if all you've ever built was high rises, you would say that you're not an expert in road building. So what does that mean? Your productions, your productivities should be significantly lower if you're not an expert in the scope. So the last one there, are quantities defined or is there risk? So what does that mean? So in previous classes, we looked at example tenders where we looked at a unit price contract where the tender gave you quantities for all the different items. You were given, you know, 10,000 tons of import material was required. You were told that there was 1,000 cubic meters of excavation. You're told that there's 1,000 meters of concrete curb to install. So that's what defined quantities, that's what defined quantities is. You're told what the quantities are. This other part here is the risk, meaning you're not told what the quantities are. It's up to you, the estimator, to determine all quantities. That can be risky. If you make a mistake, if you think there's 1,000 cubic meters of excavation, but you're mistaken and there's actually 5,000 cubic meters, your company is going to lose money. So that's what's considered to be risky. Material considerations. So properties of materials. So just in general, we're looking here. So silts and clays behave quite similarly. We'll look at a photo of this on the next slide. So silt and clay, when you excavate a trench, the trench walls can be quite steep. It's not going to cave in on itself. You get not as good compaction with clay and silt. When it's wet, you get very poor compaction. It's almost, you can't compact it when it's too wet. Like this bullet here says, it's difficult to work with when it's wet. That applies to both of those. So sand, it compacts quite well with water you supply a whole lot of water to it and it compacts even better. So sand reacts very well to water as far as compaction goes. So sand, if you were to try to dig a trench in the sand, so if you picture yourself out on the beach and you try to dig a trench just with your hand or a shovel or something, and you try to have vertical walls, how long does that stand up before it caves in on itself? Not long at all, right? Probably seconds before it falls in on itself. So you can't dig a trench in sand with vertical walls. You have to be quite shallow or sloped is another word for that. Sand is hard on equipment. So excavators, dozers, graders, it's hard on the steel cutting edges. It's hard on the undercarriages, so the tracks. It's abrasive. Sand is highly permeable. So permeable meaning water goes through it very easily. So if you dig a trench deep enough, you're going to get in sand, you're going to get groundwater coming up. Your trench is going to be wet. And you're going to have to pump it continuously in order to keep the water out. As it gets wet, it's going to fall in on itself. So water and sand in the ground is challenging to deal with. So here's a photo on the left. So there's a packer. So it's called a sheep's foot compactor. So it has little bumps on the drum. So you can tell this is quite wet. You can see how muddy, I guess is a typical word that people like to use, how dirty the wheels are on this compactor. The excavator's in the muck over here. So this clay is too wet to be working with. So over here, conversely, is the sand pile. So it's dry as a desert, it looks like. That's likely how steep or how flat this pile could be. You couldn't pile this sand up any steeper, like something like this. It would just flow down and flatten itself out. So again, we'll have a look at a couple of these in photos on the next slide. So till, so it's hard ground. It's difficult to excavate. It's quite compact. It also holds a steep slope when excavated. So again, you can excavate a trench quite steep in till. Gravel. So again, similar to sands, water flows through gravel quite easily. There's no real fine material typically in what's referred to as gravel. You'd need some silt or clay mixed in with it to prevent the water from flowing through it. So this comment here, well graded or clear. So well graded means there's rocks that are, for example, for road base, 19 millimeter road base. So the biggest rock is 19 millimeters in size. Well graded road base, which is used here in the Lower Mainland, has rocks that are 12 millimeters, 9 millimeters, 5 millimeters, 4, 3, 2, 1, and into fractions of millimeters. So that is what's referred to as well graded. It has a whole range of sizes of aggregates. Clear, when you see, whoops, when you see this word clear, so a 19 millimeter clear gravel, that means all the rock is 19 millimeters. There's no other sizes included. So that's like a drain rock. So there's a large difference between 19 millimeter road base and 19 millimeter clear. So riprap, quite big rock, or a tenby, used for protecting shorelines typically, or maybe a storm outfall structure. So you have storm water continually flowing out of a head wall, So as that water flows through, it will erode the ground surface. So typically riprap is put at the outlet head walls in order to prevent erosion. So only certain companies will transport it. So you need a steel box in your dump truck in order to haul riprap. It's very hard on aluminum boxes. Most dump trucks have aluminum boxes. Only a few have steel boxes that riprap can be hauled in. So here's the wear comment on the dump trucks. So it can be quite large diameter. It's difficult to handle and it's quite heavy. So here's the till. It looks like it's it's a well-graded material. So it's got, you know, some bigger rock, some smaller stuff. There's sands in there. It's a good range of material. It's quite dense though. It's compacted. Glacial till, it's referred to as. Here's the riprap. So quite big rocks. So this is likely a shoreline of some type. Maybe it's on the ocean to prevent erosion of the bank. So bank, loose, and compact materials. So material has different unit weights based on its condition, where it's at. So bank, what does that mean? That's the in situ condition, meaning bank material is material that's in the ground. It's the existing ground. That's bank material. Loose is after you've excavated bank. So you have an excavator, you've dug a hole. That material that you dig out, it swells, it gets bigger. The tiny little spaces in between all the particles gets bigger. So maybe you've got a stockpile, maybe you've loaded a dump truck. So it swells. We'll look at that on the next slide. So compact. So as you take this loose material and you throw it back into the hole that you just excavated, you likely will not fill the hole back up if it's compacted. So compaction squeezes all the particles together to form a denser material. So here we talk about that shrink swell that I just mentioned. So shrink. A material shrinks in size when it's compacted. So when loose material in a dump truck is dumped out of the box and placed into a hole and it's compacted, it will typically be smaller. So the volume that's in the box, if you compare that to the compacted volume in the hole volume will be less than the volume that was in the dump truck box. So conversely, swell factor. So a material swells in size when it is excavated from its native state. So when you dig the hole, that material that's coming out of the hole is swelling. Okay. So so we've talked about locating utilities in the past. We'll quickly brush through it here again. I think it's just one slide. Yeah, 2 slides. So utility locating, the best practice and the safest is to identify existing utilities prior to doing any excavating. So working around existing utilities can significantly hamper production. So if you're trying to be careful and not damage the water pipe that's in the ground, you're digging a whole lot slower than you would be if the water pipe was not there. So some methods to locate your existing utilities include these. So we've talked about dial before you dig, looking at old drawings. So old as-built drawings they're called. So a contractor previously installed the pipes through the area. So you could be given those as-built drawings to determine where exactly those pipes are in the ground. You could interview people. I don't believe I've ever done that. Hydro excavating. So there's a slide, I believe, on the next page that shows what that is. So that is, it's basically a big vacuum. So it's a truck that has a big, there's a tank on the back, and it has a big pump that sucks the dirt up into the hose, just like a vacuum does. And it can dig into the ground, and it does not damage anything that's in the ground. Another method could be ground penetrating radar. So there's systems that are available that can, you're almost X-raying the ground. So you can find different utilities that are in the ground that way. This last one here is meant as a joke. So witching rods, that's what this person's doing. That's what farmers used to do on their land to find water. I'm not sure if it works. Some people swear by it. They say it does work. I'm not sure how it works. So if you ask the question, I don't know. But again, this is meant to be a joke. You wouldn't actually go out and do this in the field. Philip, you say it works. Okay. So on the next page here. So here was the hydrovac here on the left. So there's the truck there. There's the big tank. Up in front is the vacuum system. So a hose comes off, and they can lower this hose into the ground. So this second person here has a water jet wand. It's like a pressure washer. So they blast high pressure water into the ground. That's doing the cutting. That's cutting the ground, the high pressure water. And then the vacuum is sucking it all up. So you can excavate trenches with a hydro excavating unit to find, gas services or water services, etc., without damaging the pipes. This is the ground penetrating radar. So the person walks behind and it scans the ground as they walk. So you go back and forth across a work zone and you can determine what's in the ground. So slopes. So excavation volume depends on the slope of the material that's left. So we just went through some examples, not examples. We went through the exercise from week 3 where we were using one-to-one excavation slope. So you can imagine if we did not use that one-to-one slope, if we used vertical trenches, how much that vertical trench would reduce the amount of excavation that you have to do. So it's a significant amount. If you can excavate vertically safely, then you don't have to excavate nearly as much, which is cheaper. So exposed slopes behave differently when excavated. So an exposed slope of tills or clays will typically stay like that. So a slope, so maybe it's a one-to-one slope of till or clay, it'll stay like that basically forever. Whereas sands, they will slough. They will start to, the sand will flow to the bottom of the slope, basically. Especially when there's rain happening, an exposed slope will start to erode, and the material that's on the slope will end up in the bottom of the excavation. Water that's in the ground makes the slope less stable. So that's a safety issue. If the water table is high enough that you're excavating into it, meaning your slope is wet from groundwater, then that slope is less stable than if it was dry. So how flat or how steep your slopes are determined by WorkSafe BC requirements as well as a geotechnical engineer. So let's look at a couple different ways to reduce the amount of sloping in an excavation. So here's our excavator. So here's the trench down here. This cage down here is called the trench cage. So this allows you to excavate vertically. Now, if they stacked some cages on top of each other, they wouldn't need to bench like this. So what they're doing here is they have a cage in the bottom, and then they're sloping, or they're benching the rest of the slope up. Similar here. Here's their shoring cage. They've benched here, so they've excavated this piece out, and then again and up and out. So this trench line looks like it was under groundwater. That's what this system is here. It's a system of wells that are jetted into the ground. This is a pump, so it's going to pump on it's going to suck on each of these hoses all the way along and pull the water out of the ground and discharge it out this hose. So what that does is it dries out the groundwater that's in the trench. These systems are quite effective, but they're very costly. So there's a system, they're typically called well points. So there's a system on either side of the trench. So it runs the full length of the trench. Looks like it even maybe turns the corner there. So excavation shoring. So shoring is for temporary support of excavations to enable safe access. So if the crew needs to get into the trench, it needs to be safe. WorkSafe BC says so. So if a person needs to be in a trench, it has to be either sloped or you need to use shoring. So the shoring cage, as we saw in the previous pictures, or sloped or benched. So the cage would need to be, so the second bullet here, cage needs to be sized to fit people inside of it, plus the materials that you're going to be putting in. So the cage needs to be wide enough, if we go back up a page here, this cage needs to be wide enough to fit the pipe in it, as well as the people that are working in it, as well as working room between the pipe and the side of the cage. Right, so you have to keep that in mind. These bars here are called spreaders. So you can get different lengths of those spreaders to increase the width of your trench gauge. So shoring cages are designed to suit the soil conditions that they're in. So this may need is incorrect. They are designed by structural engineers, shoring cages. So you can refer to WorkSafe BC when required. There's a section in the WorkSafe BC regulations that deals with sloping. It's section 20.78. So you can go onto WorkSafe BC's website and have a look at that. It's in the excavation section. So it tells you, based on the type of material that you're in, so the type of ground, tells you how steep or flat the slopes would need to be if you're sloping. Yeah, so you can read up on that. We're not going to get into that in very detail today. Here's a couple more photos of shoring cages, or shoring boxes they're also called. So these two are shoring cages. So again, you have the steel sides with spreader bars here. So this would be picked up by an excavator and loaded onto a truck and taken away. It's also installed with an excavator. It's picked up, put into the trench, and then the crew can get in and start working. Same thing here. So with this one, it's slightly different. It's not a shoring cage. that you could pick up and put it on a truck. It's built with sheet pile walls. So there's individual steel plates that are pushed into the ground and they interlock together. So you can have an infinite length of trench that's shored with sheet piles. If you have enough sheets, you can continue to put them in the ground. Of course, you need them on both sides. Again, you have a spreader bar type system to help support those sheets. So these sheets are actually driven into the ground. They go well below the excavated surface. Whereas the shoring cage, the bottom of the cage is sitting on the bottom of the trench. It's not buried in the bottom of the trench. That's one of the main differences between a sheet pile system and a cage system. The sheets are pushed into the ground. So there's different calculations here. So sloping, shoring, according to WorkSafe BC. So these are just a couple example photos, things you might see in the WorkSafe BC regulations. So if you had a cage, you're told the maximum slope you can have if you're going to slope above that cage. So shoring must be adequate for excavation depth H, so there. So depth H cannot exceed 6 meters. So if you have a hole or a trench or anything that you're digging that's more than 6 meters deep, you have to hire an engineer and have them design the shoring system for you. That's a requirement of WCB. Bruno, you have a question? Is there any factor that you use for compaction? Relationship between volume for each type of soil? The volume calculations of exercise 3 and 4, subject compaction. So, yeah, I can't specifically remember exercise 4. So, let me just have a quick look here. What does it say for that assignment? So exercise 4, you were to calculate the cut and fill volume based on cross sections. So no, you weren't supposed to use any compaction factors there. So it's just a straight end area calculation. Further down into question 2, where it talks about how many tons of subbase, you were simply doing a conversion using the tones per cubic meter that I provided. So I said use 2.3 tons per cubic meter. So that's how much gravel you would purchase. So fill volume of cubic meters times 2.3. So typically compacted road base and compacted road subbase is a Proctor value of about 2.3 tons per cubic meter. So that's 2,300 kilograms per cubic meter. So that's why I typically suggest either 2.2 or 2.3 as your conversion factor. So that's compacted in place volumes converted to tons. Sand would be less than that. Silt and clay would be less than that. Probably in the 2,000 kilogram per cubic meter range, somewhere in there for silt and clay. Sand is probably maybe 1,800 kilograms, so 1.8 tons per cubic meter. Those are good rules of thumb anyway. Does that answer your question, Bruno? Okay, so next sheet, turn my page. Sloping shoring continued. So again, these diagrams are right out of the WCB regulations. So again, if you go onto WCB's website and you look at section 20.78 specifically, you can find more details about how all this works. So depending on load cases, you can do different things with your sloping, different material types. You can bench, right? You can slope and bench. So WCB tells you how all these work. So I'm not going to get into that now. It'll eat up too much of our time, which we're already behind where I want to be in the class. We won't have time to do the example afterwards. So have a complete plan to avoid digging an expensive hole. So some things that I still do as an estimator, I've been doing this for 20 years, over 20 actually, sketching things on your drawings. So sketch out your proposed excavation on the drawing. So for instance, our oil interceptor, you could sketch out where and draw it to scale. You could sketch out where that excavation is going to be. So if you drew that to scale, if maybe there was a building that was, 2.5 meters away, you could determine that your excavation would be underneath that building if you use one-to-one slopes. So that would tell you that you would have to do something different in order to protect that building. So using your pencil and drawing all over your tender drawings is a good idea. You never have to give those back, they're yours. So draw all over them, make notes, use colors, anything to help you understand what's going on the drawings. So some other notes that I have here. So do required cut slopes fit? So that goes to my oil interceptor example with the building that's close by. Maybe it's not a building, maybe it's a water pipe that's in the ground 2 meters away. Is there physically room to make that one-to-one cut slope and not undermine or expose that water line? Exposing the top of a pipe is fine. Digging underneath of an existing pipe is a no-no. You shouldn't do that unless you've supported it in some fashion. So again, using your pen and pencil on your drawings to draw things to scale is highly recommended. Okay, so any other questions on the PowerPoint? Okay, so let's turn this off. There we go. Okay, so it is 8:18 according to my clock. Let's take a 10-minute break so I can refill my water cup, and we'll come back and do the in-class example for today's lesson. So this in-class example is very similar to the exercise or the assignment that you're going to be given. So that's why I wanted to have enough time to do this in-class example. So I will see you back here at 8:29 in 10 minutes. I will pause the recording. Okay, we're back. So I've just posted to Learning Hub the in-class lesson. It's 2 pages that we're going to go through right now. So feel free to download that. We'll go through it on my screen here. If I can share my screen, there we go. So this is what it looks like. So lesson 5 discussion. So we're going to do an earthworks estimate for the Oil Interceptor. So the same Oil Interceptor that we've been working with all along in this class. So we're not going to do this in groups, we're going to do it all together. So first thing we're going to do is come up with a list of activities. Then for those list of activities, we're going to come up with quantity takeoffs. We're going to figure out how many loads of material to haul off-site, how many loads of import material to haul on to the site, and these are the parameters that we're given to work with. So before we go through all those, well, maybe we'll just read through them here quickly. We'll go through them again as we go through this example. So our cost estimate, so we're going to use the following information. So we have dump trucks with pups, so those are the small trailers. So this haul unit can carry 10 cubic meters of material. So that's when we're hauling spoil off-site, carries 10 cubic meters. And that truck charges us $125 per hour. So we have a disposal site, so where this truck is going when it's hauling off the spoil, that's 45 minutes away. And the fee to dump the truck is $25 per box. So if we have a truck and trailer, it's $25 per box. So of course there's 2 boxes, right, for each load. So we have 3 dump trucks. Material is delivered. So imported material, so our gravel that we're going to buy, is delivered to our job site in 40-ton truck and transfers. So again, that's a truck with a bigger trailer. So 40 tons of gravel. The cost of that gravel is $18 per ton plus PST tax. So we need to add PST. So an excavator, so we have an excavator that can excavate and load this 10 cubic meter haul unit. It takes about 20 minutes for that excavator to do that. Our excavator costs us $110 per hour. So labor and or operators, they're both $45 an hour. So labor is 45, the operator is also 45. So we have a plate tamper, so that's a small compactor, something that maybe a laborer would walk behind. So it's a labor unit. It costs $25 per hour. So a big compactor, so vibratory compactor that an operator would ride on, is $70. So the crew of an operator and laborer can place and compact fill at a rate of 10 cubic meters per hour. So our compaction equipment with an operator and laborer can compact 10 cubic meters per hour. So getting down here at the bottom here, the Oil Interceptor, so to buy it costs $5,000. That amount includes delivery, but we have to add tax. So again, we're adding PST. The size of the concrete box, so dimensions here, are that are noted here. So 1.1 wide, 2.6 long. And then, so the depth, so this is slightly different than what we've been using. The depth is 0.85 meters below the invert. Previously, we used 1.05. So this has been changed slightly. So 0.85 below the invert. Overall height of 1.8 meters. So down here, so our conversion factor to determine how many tons of gravel we need, we're going to convert 2 tons of gravel for every cubic meter of fill that we want. So for example, if we determined that we needed 10 cubic meters of gravel, so we would go 10 times 2 tons per cubic meter, means we would need 20 tons of material to buy. So using all of this information, we're going to determine what the cost is to buy the oil interceptor, to dig the hole, to backfill it with gravels, and compact those gravels. Okay, so the first part of the lesson is let's list some activities. So if I go over to my spreadsheet, and I'm just I'm hiding the words so you don't see them all as soon as I bring the spreadsheet up. Okay, so I'll share the spreadsheet. Here we go. So we're going to look at 5 different tasks. So let's say we've already laid out the oil interceptor. So one of our tasks isn't going to be to do the layout. We're going to say that's already done. We're also going to say that the exposing the existing utilities has also already been done. So that is not going to be one of our tasks either. So we know there's nothing in the way and we've got our layout completed. So we know where we're going to dig. We know there's nothing in the way. So what do you think would be our first activity that we want to list here? You're kind of given a hint by what the crew is going to be. Anybody have any guesses? No guesses? Excavation, there you go. We need to dig the hole first. Okay, so we're going to come up with quantities later. So we're going to determine what all the tasks are first. So we've dug the hole to where it needs to be, down to the depth that it needs to be. So we've got all this excavated material now. So what should we do with it? Right. We need to haul off our waste because our oil interceptor is in the parking lot. So we need to have imported gravel backfill to backfill our oil interceptor. So we're not going to put any of the excavation back in the hole. So we need to dispose of our excavated material. So we've disposed. So now, what do you think is next? So you want to, Ivan, do you want to fill the hole next? Okay, we're missing a step. We want to put the oil interceptor in the hole, right? Before we backfill, we want to put the concrete box in. But you're right, after that is when we put the granular backfill in. So we've dug, we've hauled off the spoil, we've put the concrete box in, that's going to be in our fill quantity. You're right, Ivan, we do need 100 millimeters minimum of gravel underneath. We're going to say that volume is in our place fill volume. So we're not going to separate it into 2 items. Good question though. So what is last? So we've we've put the gravel in the hole. Exactly, we need to compact that gravel. Okay, so I'm thinking maybe we need to look at a sketch here, trying to determine the best way to do this to calculate this quantity. So let me flip back over to the scratch pad here. Okay. So if I'll draw this bigger so that it's easier to see. So that's our oil interceptor. So in the lesson handout, so the information that we were provided at the bottom of the page, we were told some information on the oil interceptor itself. So we were told it was 1.1 meters wide, 2.6 long. The invert, so that's the invert of the pipe. So there's the invert. We were told the distance to the bottom of the box from the invert, so this distance, is 0.85. So this here, 0.85. Okay, so what else do we have here? Okay, so if we look at, again, we're going to look at this in two directions, this way and this way. Exactly the same thing that we did with the exercise 3, where we looked at the volume of the excavation there. This one's slightly different because we're not going from the bottom of subbase. We're going from, I'm changing it slightly. We're going from finished grade. We're going from the rim elevation is the top of our excavation. Okay, so I need a couple of these. So not the utilities, so we have the oil in the X direction. Okay, so again, we have this box here. It's not a pipe, it's a box. The box in the X direction, so this one here, we're saying the box is 1.1 meters wide. Again, we want some room there. I'm going to use the same 150 millimeters of room. So our box width, or sorry, our trench width at the bottom will be 1.4. So I've simply added 300 millimeters to the 1.1 meter box width. Okay, so what else do we need? We need a rim. We need, I'm going to draw a line out here. I'm going to say this is what the pipe invert is, because we're given this information also. So invert pipe. So right off of our drawing, I'll read the correct numbers this time. So rim is 6248, and the inverts were, they were both the same, the in and the out, 60.82. So if I grab a color and I shade the bedding underneath, we'll use 100 again for that. So let us calculate the overall depth of our excavation. So that's the bottom of bedding. So we go 62.48, 62.48. We subtract the pipe invert, 60.82. So that gives you the height from between those two surfaces. We add in the 0.85 that the question tells us, the information that we're told. So this here is 0.85. So I need to add that. And then lastly, we need to add the 100 millimeter thickness of bedding. So I'll add 0.1. That gives us a depth of 2.61 meters to the bottom of the bedding. So now, so that's the depth. We have this width here. So then the last thing we need is this width of the triangle here. So again, does the question tell us to use 1-to-1 slopes? Yeah, it doesn't actually tell us that, but we're going to assume it. So we'll assume 1-to-1 slopes, meaning the depth is the same as this horizontal width here. So that means this is 2.61. Okay, so then that allows us to determine, again, this length up here. So what's that length? It's 2.61 plus 1.4 plus another 2.61. So if I just add those all together, so that the length of this blue line is 6.01. Okay, so that's in the X direction. So again, if we look here, we're looking in this direction. So what we've done is, I take my pencil, we've done a typical cross section, something like this, looking in that direction. So now we want to do a similar exercise looking in this direction of the box. So we're going to create another cross section of the box, but looking in the Y direction. So I draw the box on here. So we are Oil Interceptor in the Y direction. Okay, so from our sketch here, we said the length of the box in this direction is 2.6. So again, we're going to add some room. Yes, that's correct. 1.1 plus 0.3. Same kind of calculation for this direction. So it's going to be 2.6 meters of the box, and we're going to add 0.15 to either side for working room. So that'll be 2.9 overall width. So things that don't change are the rim. So 62/48. The invert of the pipe. So this here, pipe, invert, that does not change. The depth to the bottom of the concrete box below the invert of the pipe does not change. Sure, you can take 0.2 both sides, that's fine. Okay, so what this tells us is if the rim, the pipe invert, and this depth don't change, what that tells us is the overall excavation depth doesn't change, right? So we don't need to calculate it, we just need to copy it from our previous cross section. Still 2.61. The difference is the length of the box in this direction. That's the only difference. So again, up here, 2.61 meters. So I'll color in the bedding just for completeness. So lastly, you're determining the length of that blue line. And it's simply 2.61 plus 2.9 plus 2.61. So I'll do that. 2.9. So that is 8.12. So length of the blue line is 8.12. Okay, so it's the same calculation that we did before. So what we're going to do is we're going to use this length in our Y direction and this length in our X direction. If we multiply those two numbers together, that gives us the area looking down on the top. That's the excavated area. So with these 1-to-1 slopes going up, right? And in this direction, 1-to-1 slope going up, that's the length and the width on the ground surface using our 1-to-1 slopes coming up from the bottom. So obviously the hole on the surface, you know, up here somewhere, isn't going to be 1.1 meters by 2.6 meters. It's going to be bigger than that because we have 1-to-1 side slopes coming up, right? So we're sloping up. So our excavation is quite a bit bigger than the excavation at the bottom, that footprint. So if I simply take those two blue calculated numbers that we had, so in the Y direction, we had a blue length of 8.12 meters. And in the X direction, the blue line length was 6.01. So now we go 8.12 times 6.01. So those are both meters. So again, that's the top area. We need to add to that the bottom area. So what is the bottom area? If we go back to our cross sections. So the 2.9 is one length. So let's call that our green length, because we've already colored it green. So in the Y direction, the length at the bottom of our excavation is 2.9. And on the X, the other one, once you do this a few times, it won't seem nearly as complicated. So this one is simply 1.4 for the X. So we'll go back to our main sketch here. So that was the top footprint area of the excavation. So the bottom is simply, we need to add to that the 1.4 meters and the 2.9. So we add, so this will give us an area, this will give us an area. If we add those two together and divide by 2, it gives us the average excavated area for our oil interceptor. Then by simply multiplying by the overall depth of our excavation, it'll give us the volume, the cubic meters of excavation. So if we go, what was our depth? We calculated that to be 2.61. It's the same on both. So if we multiply 2.61 times this calculation, what does that give us? So if I go 8.12, 6.01 times, then I'll go 1.4 times 2.9. So this was about 48.8, this number. This is about 4. So if I add those together, divide by 2, I get an average end area of about 26.4. So multiply by the depth, 2.61, gives you approximately, I'm going to round it up. I'm going to say it's 70 cubic meters. It's 68.98. So I'll just round it up to an even 70. Okay, so that is our excavated volume. Okay, so let us go back to the I'm blanking out some numbers here so you don't you don't see everything before I want you to see it. Okay, so if we Okay, if we go back to the spreadsheet, here we are. So here is our 70 cubic meters, right? So that's what we just calculated. That's our excavation volume. So I'm reading through the information that's provided in the example. So those dozen bullets that were at the bottom. So I'm looking, oh, there's the excavator. Okay, I couldn't find it there. Okay, so we're told that our excavator can excavate and load 10 cubic meters in about 20 minutes. So we're digging, maybe I read the wrong thing here. So we've got 70 cubic meters. We can do 10 cubic meters in 20 minutes. So we have 70 cubic meters. If I go, okay, so 70 cubic meters. We can excavate 10 cubic meters. So if we divide by 10 per 20-minute time frame. So what the calculation is here is 70 divided by 10. And then we're multiplying by 20 minutes. So it's 140 minutes. So 140 minutes to excavate the 70 cubic meters. So 140 minutes divided by 60 minutes in an hour is approximately, it's 2.33. I'm going to round it up to 2.5. Okay, so we've got 2.5 hours for our excavator, 2.5 hours for the operator. So the operator is in the excavator. And then we have a laborer. So we've got a person, typically when you're excavating, there's a person on the ground, kind of right next to the bucket, watching what the excavator is digging. So to make sure that nothing's hit. So that's kind of what this extra person does. Could also be doing other things like, telling the excavator operator that, they've dug deep enough. They're at the location where they need to be. So this person kind of does a few different things. So that's why he or she is there. So we're given, let's not get into the pricing quite yet. We're calculating our quantities here first. So we've got 70 cubic meters of excavation. We said haul off was next. So we had spoil. So we're getting rid of our 70 cubic meters. So in the notes at the bottom, it says our dump truck with the pony trailer or the pup trailer. So that haul unit can carry 10 cubic meters per load. So if we divide by 10 cubic meters, that'll give us the number of loads, right? So 70 divided by 10, put another space in here, leaves you with 7 loads. So that's 7 trips of the truck and trailer that needs to be accounted for. So how long does it take that truck to go and come back? So we've got this backwards, units are first. So 70 cubic meters is our haul off. Okay, so we have 7 loads. So in the notes, it says, the second bullet says the disposal site is 45 minutes away. And then it talks about the cost for each box. Okay, so we need to determine how many hours of trucking we need in order to haul 7 loads. So we're told disposal site is 45 minutes. So I'm going to work in hours here. Right, Karen Beer, 45 minutes. So 45 minutes is 0.75 hours. Hours. Okay, so that's for the truck to go to the dump site. So we need to add to that the time to drive back to the job site. So that's the same amount of time. So 45 minutes there, 45 minutes back. So we're not done yet. So we need to add in some additional time here. For loading and dumping. So we've got, we're told that the excavator can load the truck in 10 minutes, or sorry, check that, 20 minutes. So 20 minutes is 0.33 hours. So the truck is sitting there for 20 minutes while the excavator is loading it. So the last thing that we want to add is the time that it takes the truck to dump. So there's a number of minutes that the truck is at the dump site that it needs to back up. It needs to go where the people that own the dump site, where they want the truck to dump. So there's some backing, there's some maneuvering, there's physically dumping both boxes. It does take time. So we're going to add in another just 10 minutes for dumping. So 0. How many, what is that? I'm rounding this. So hours. So 10 minutes is approximately 0.17 hours. So 10 divided by 60 is all that is. So when we add that up, so 0.75, 0.75, 0.33, and 0.17. So it's 2 hours per round trip, or per cycle, it's also referred to as. So if it takes 2 hours to do 1 trip and we have 7 trips to make, how many hours of truck time do we need? So we got the units right here. So of course it's 7 loads times 2 hours per load. Right? 7 times 2. How about the fees? So we're told in the information at the bottom that disposal 45 minutes away, and there's a tipping fee of $25 per box. So how many boxes do we have? We've got 7 loads. How many boxes? 14, exactly. So 2 boxes per load, right? Okay, so we've got installing the Oil Interceptor is next. So let me So we've got a crew here to install. So we've got an excavator to pick up the Oil Interceptor. We've got an operator, and we've got some people on the ground to help hook things up, unhook things. You have a question, do you always have 2 boxes per load? No, it depends on what you're hauling with. If you're hauling with just a truck, then that's 1 box. But in our example, we're told we have a truck with a pup trailer. So it's 2 boxes, the truck box and the trailer box. Sure. Okay, so I don't think I actually tell you how long it takes to install the Oil Interceptor. Excuse me. So we've got an hour for our crew to set the box into the bottom of the hole, and we've got the Oil Interceptor here. So one lump sum, right? We were told the cost of the Oil Interceptor was $5,000. So you can see here that I've multiplied by 1.07 that adds the PST, right? 7% PST. So the purchase cost is $5,350. Okay, so moving on here. So we've got the concrete box in the hole. So now we want to backfill. So quantity, so this is cubic meters here for units. So our backfill. So what is that quantity going to be? So we said our excavation. So excavation is 70 cubic meters. So that's how much we took out of the hole. Now, since we've excavated, we've put this concrete box in there. So when we're putting gravel back in, we're not going to fill the concrete box with gravel, right? So to calculate the volume of fill that we're going to backfill, we need to subtract the volume of that concrete box. So minus oil volume. So what's the oil volume? Well, we're given the dimensions of the concrete box in the information. So we're told the box is 1.1 meters wide by 2.6 meters long and it is 1.8 meters tall or deep. So we simply multiply those three numbers together. That'll give us the volume of that box. So 1.1, 2.6 times 1.8. So that's 5 cubic meters. So if we go back up here, we're saying excavation is 70. We want to subtract the volume of the box, which is 5. So if I go 70 minus 5 and I make it visible, we're saying the backfill is 65 cubic meters. We're going to ignore swell here for this example. We're trying to keep this one basic. Yeah, we're going to ignore it. So right. So how long does it take to backfill? Actually, let's do this calculation first. How many tons of gravel do we need to buy? Well, we said we needed 65 cubic meters, and we're told in our handout to use a conversion of 2 tons per cubic meter. So you're simply going the required fill volume times 2 tons per cubic meter will give you the total tons that's required. So equals 65 times 2, and again, if I make it visible, 130 tons. So now, hours of backfilling, how long does that take? We know the quantity of backfill. We've purchased the backfill, but we need to know how long our crew will take to place that backfill. So I'm looking through the notes here. So it says, there's a bullet that says a crew of operator and equipment can place fill at a rate of 10 cubic meters per hour. So we want to go 65 divided by 10 for both of these. So we've got 65 cubic meters, and we're placing at 10 cubic meters per hour. So that means there's 6.5 hours of this crew. So lastly, yes, we need to compact that fill. So again, here we've got the units, make them visible. So it's the same number, right? Not sure why that one's red. We'll make it black. So let us have a look at our crew here. So we've got a laborer, a compactor, and a tamper. So the laborer would be using the plate tamper, and the compactor, we should really have an additional operator here. So the laborer is using the walk behind tamper, and the compactor is being operated by an operator. So it's the same hourly rate as the laborer. So again, we look into the information that were provided at the bottom. Oh, it's the same. Compaction is the same. It's 10 cubic meters per hour. So if we go equals 65 divided by 10, make that visible. So there's our time for the compaction. So this would be happening at the same time as this, as you're placing your compacting. We're showing them separately, just to make it clear what's going on. But this operation in the field, when it's actually done in the field, placing and compacting are done at the same time. So the excavator is putting in buckets of gravel. The crew here is going around compacting it. So the excavator dumps the bucket, spreads it around. The crew down here compacts it. So they work around and around the concrete box until it's completely backfilled. So I've already punched in my hourly rates. So these are given to you in the question, all these dollars per hour. This dollars per box is given to you. So that you don't have to determine that. Those are all given to you. So then you're multiplying these lines out. So the hourly rate times the hours. Hourly rate times the hours. So I've got again, you could absolutely use an Excel spreadsheet here. It will make it quicker. You can copy and paste things, pull your formulas down, write the formula once and then copy it down. So if I make these visible, just want to make sure these are all correct. So we've got 1 hour for everything there. So there's our purchase cost of the Oil Interceptor. That includes 7% PST, right? We had to multiply by 1.07. So down here to placing the fill, again, you're simply multiplying straight across. 110 times 6.5 gives you the total dollar amount for each one. So down here, so we're given the purchase price of the backfill is, it says in the notes, it says $18 per ton plus tax. So again, I've added PST here. So 18 times 1.07 will add 7% PST. So the new per ton rate is $19.26. And simply multiplying those two together. So quantity times unit rate gives you the dollars. And then the same thing down here. We're going to extend that down. Okay, and somewhere down here there should be a total. I guess it's this one. So that looks correct. So you would simply total that entire column and get the total cost. So maybe if I make that one red. So there's your total cost to purchase, excavate, install, backfill, and compact the Oil Interceptor. So any questions? No? Okay, a few of you asked questions along the way, so that's fine. So that's basically the procedure that you're going to do for the exercise or for the assignment today. Rodney, do we need to add gap to the hours? What do you mean by gap? No, don't add extra hours. You can round up, but don't add extra hours. No, don't include delays in your estimate. Okay. So let me, okay, I'll stop that. So what I need to do is post the assignment to the Learning Hub. I will do that right now. So week 5. So of course, as per all the previous weeks, feel free to ask questions. Email me with any questions that you have. Week 5 assignment. Yes, there is, excuse me, a midterm next week. Let me just post this assignment and then I'll talk about the midterm. Just give me 1 minute here. 5. So I'm going to post a Word document for the assignment so that you can insert Excel spreadsheets anywhere you choose, anywhere that'll fit. So feel free to add to that Word document. Okay, there it is. And okay, so that is posted right now. The Excel file I'm not going to hand out. You can watch it on the video. You can look at it on the video. I don't want to hand that out. For your assignment, just start with a blank Excel spreadsheet. You don't need anything special. Just titles, column titles like task, you know, material or description, units, quantities, rates, totals, that type of thing. Okay, so I will scan all of my sketches and things that I did here, and I will post all of these to Learning Hub as well. So those will be up shortly. Let me talk quickly about the midterm. So the midterm is, I'm looking at it here right now. It's basically the exact same thing that you're doing for the assignment, for this week's assignment. It's another estimate like that. So some excavation, you need to determine, you know, hours of the crew. You need to determine how much gravel you need to buy. So there's haul off, there's things like that. So it's nothing that you haven't seen already. So it is, I'll mention that it's open book. The midterm is open book. Not that I could stop you from looking at all your notes, but it is open book. So there's no issues with looking at, you know, past assignments, past notes, etc. Be aware though that there is a time limit. It is 2 hours long. So you have to finish within the 2 hours and submit, because we do have a lesson next week also. It's a short lesson, but there is a lesson. Any questions on the midterm that's going to happen next week? No? Okay. Okay, so I will scan my sketches that I did tonight. Yeah, Pardeep, your comment about, according to the outline, it covers the first 4 weeks. That's not entirely true. So it references the drawings that you have. So you will need your drawings. So it deals with an item that's on those drawings. So you have to have your drawings available to you. All the other pertinent information is given to you in the question. I'm just reading through it here to see if there's anything that is misleading. Yeah, most of what we learned today is the bulk of the question for the midterm. So there are other things that deal with cross sections. That's a very small part of it. So you're calculating quantity takeoff. You're listing your work activities. You're costing your quantities based on productions that I give you. And then you come up with a final estimated cost for the question. So it's very similar to the example that we did today, and it's very similar to the assignment that you will do this week that I just posted to the Learning Hub. You 2 hours should be lots of time to complete the midterm. Uploading your completed document only takes a couple minutes. It can be a Word document. You don't need to change it in any other device, or sorry, any other file type. So, I mean, there might be a couple minutes leeway, but you're not going to have 2.5 hours. It'll be a 2-hour exam. No, normally this class is done in person, so it's all by handwriting. So it's to be able to use an Excel spreadsheet during the exam is a significant benefit that I'm not going to say no to, but I'm not going to provide it to you. No, it's not multiple choice. You're calculating quantities, you're determining costs based on productions, number of hours of crew you have to figure out, that sort of thing. No multiple choice. It's calculations. Estimating is all math, right? So you're doing math for the entire exam. Any other questions? No? Okay, so I'm going to stop the recording. What's the starting time? We'll start right at, as soon as I do the attendance next week. So class starts at 6:30, so we'll do attendance, and then I'll post the midterm to Learning Hub. So probably from, say, 6:45, you'll have 2 hours from then. So it'll be something like 6:45 to 8:45 of actual test rating. But don't be late. Show up before 6:30 as usual. Okay, so I will stop the recording.